Liquid level system problem. Homework 7, problem number 2. Cross-section area of the tank, linear resistance of valves, initial conditions, and pump head were given. Units are based on fluid head in meter. You were asked to find differential equation of motion of two tanks and use Simulink to find the history of the liquid level H1, H2. Then transform the differential equation into state space form and find the solution and compare with the differential equation solutions. So in order to establish the differential equations governing the behavior of these two tanks, we will be using the principles conservation of the volume. Let's start with tank number 1. Choose the control volume. We know the read in and read out can be calculated based on the level difference. Rate of change of fluid volume in the tank is equal to flow rate in minus flow rate out. Level difference divided by resistance. Let's name this equation number 1. Similarly, we can find differential equations for tank number 2. Control volume. Flow rate in for this tank is the same as flow rate out for tank number 1, Q2. Flow rate out, Q3. Cross-section area times height rate change the rate is equal to flow rate in minus flow rate out. Equation number 2. So based on these two differential equations, we can construct the Simulink model. To do that, first, we want to reorganize equation number 1 and number 2 so that we can solve for the highest order derivative term. We will place that highest order derivative term on the left side of the equation by dividing a and both sides of the equation. For first equation, divide a1, we find equation number 3. Based on equation number 2, divide a2 at both sides, we got equation number 4. So now let's move to Simulink model environment to do this simulation. At least these two equations here. And I'm planning to build the model for the tank number 1 on the top and bottom for tank number 2. Obviously, we will be using integrator block. To do the integration, the signal going into this block will be dH1 dt and out will be H1. We will do same thing for equation number 2. dH2 dt and H2. To monitor the level height history of H1, H2, we want to add scope here with 2 axes, one for H1 and one for H2. Now we can start to construct the right-hand side of the equation for tank number 1. we see there will be division and minus. That means we will be using math operations, addition block and gain block. Equation number 1, the terms will be divided by A1, so we have this 1 over A1 as a gain before we reach in dh1 dt. And we have this minus, so we can change the signs of addition block. The input to this plus sign will be a minus divided by R1, so we need a copy of addition and a copy of the gain block. Now we change the gain value to 1 over R1, and minus sign will be delta H minus H1. We'll change the order. And delta H come from step input, we name it as delta H. Out of this summation will be divided by R1. And then H1 will be feedback to subtract from the delta H. And finally, we also have a minus H1 over R2 term. So make a copy, flip it, change this A2 1 over R2. Then H1 over R2 will be inverted and added onto the previous term. So these whole blocks represent our equation number 1. We can do similar thing for equation number 2. Make a copy, change the gain to A2. We need addition block. H1 over R2 over here minus H2 over R3. We need a gain block which is 1 over R3. Times H2 subtracted from previous term. Then we realize equation number 2. Check the signal flowing. Make sure both equations are implemented. You can rename any of these blocks. And then we need to assign initial values for the pump head. And the water level for first tank is 1 meter, for second tank is 0, empty originally. Next, we need to assign the values to all these parameters we are using, R and A. Do not forget to check. Use display text as a click callback. Then when you double click them in workspace, you will generate all these values for these parameters and run simulation. We see none of these two tanks reach the steady state fluid level. So we want to go back to change the simulation time. Increase to 1000 seconds. Run the simulation again. Then we see both tanks reach steady state. For first tank and both the second tank, they both reach 6 meters after 200-700 seconds respectively. So in order for us to plot this output in other software or in MATLAB, have better control, you can use output block here. We can drag in clock and max it with H1 and H2. Let's change the input numbers to be 3. The first one will be time, second one H1, third H2. They will be max and then put into the one output file. Run the simulation again. We see in workspace there is Y out generated. First column store time, second and third H1 and H2 respectively. Then we can plot the first column versus second column with blue and first column versus third column with red and dashed line. So we see the results again. So step C, you are asked to transform the differential equation motions into state space form. It is matrix form characterized by A, B, C, and D, respectively. So here, the first equation is called state equation. Second equation is output equation. So for this problem, let's set state variables h1 and h2 as state variables, give a new name x1 and x2, and u, which is the pump head delta H as input. And we want to use y1 and y2 to represent output. Of course, we are interested in getting the output h1 and h2. The equation number 3 and number 4 will become this matrix form. State equation, first derivative of the state variables is equal to matrix A times state variables x1, x2 plus matrix B times input u. Make sure the matrix size matching so that we'll be able to do this operation. Fill in the numbers minus 1 over R1 A1 minus 1 over R2 A2 times x1 plus 0 times x2 equal to 1 over R1 A1 times u. Got the first equation. Similarly, we can write out the second equation in matrix form. Next, after we find x1, x2, we want to write the output equation. Here, we are interested in both y1 and y2, which is x1, x2, or h1, h2, respectively. The first equation, y1 is equal to x1, the right side of the matrix. y1 is equal to x1 plus 0, x2 plus 0, u. y2 is equal to x2. Then we found A, B, C, D matrix for state space form. Based on this, we can construct Simulink model. Let's come back to a new Simulink model here. To construct Simulink block diagram based on state space model, we need space block from continuous sublibrary, step block from source sublibrary, and scope from sinks sublibrary. Connect them, assign values for input, delta H, assign parameters A, B, C, D, and initial values 1, 0 to state variables. Before we run the simulation, we still need to assign values to A1, A2, R1, R2, and calculate for A, B, C, and D. You can do this in MATLAB script or type in model and use click callback function as we did previously. Here, I'm using MATLAB command window to generate all these parameters and matrices. After we're done, run the simulation, we find results are the same as we obtained before.